Hello, in this video we will look at Faraday's law, and Lenz's law, and how they relate to electromagnetic induction. Now, Faraday's law states that the magnitude of the induced EMF is proportional to the rate of change of flux linkage. So, because the magnitude of the induced EMF is proportional to the rate of change of flux linkage. Okay, so there's some very strange words going on there, especially this flux linkage bit. Okay, now what I'll do now is I'll rub this off and we'll look at where this comes from and what equation it relates to. Okay. Right, so we'll start with flux. What is flux? So, flux are simply magnetic field lines. So here is some flux. There you go, that's magnetic field lines. Okay, and that's given by this symbol here, phi. That is flux. Okay, now what else do we need to know? Well, we also need to know what happens if the flux is contained within an area. So let's take some flux here, and let's have an area here. So this is an area A. So we're now containing it. But now we've got something called flux density, and flux density, which is flux there divided by the area, is equal to B. And you should be familiar with B, because B, as well as being the flux density, is also known as the magnetic, right, let's try and do some spelling better today, magnetic field strength. Therefore, if phi over A is a flux density equals B, we get the relationship that the flux is equal to the magnetic field strength multiplied by the area. Now, we also had a term in Faraday's law, this idea about linkage. So let's say linkage is ultimately, or flux linkage, flux linkage can be thought of as, if you like, that's an area, that's a single coil of conductor. You've had more coils, okay? That's far more useful for generating an EMF and electricity. So we've got lots and lots of coils there, and let's say we've got n coils there, and we find that flux linkage, which you could call is equal to n times the flux, which could be thought of as NBA. So in Faraday's law, when it talks about flux linkage and rate of change of flux linkage, this is what you're talking about. You're talking about number of coils, you're talking about flux, and you're talking about an area there, NBA. So let's now formally write Faraday's law as an equation. So, as an equation, Faraday's law can be expressed as the induced EMF. Well, we're going to make the proportionality 1. So the induced EMF is equal to the rate of change. Rate of change relates to time, so we're going to have this is the flux linkage, n psi there, and the rate of change, we could write that as dn psi with respect to time, and we're going to put it in the negative direction, because Lenz's law says the induced EMF is in such a direction as to oppose the change causing it. So that makes that negative. That's one way of writing it. Another way of writing it, more familiar with the IB syllabus, is you write it as minus, little triangle there, delta rad change of divided by the change in time. Sometimes the n is taken out, but of course n can change it, but sometimes the n is put in front of that. And also we can actually represent it simply, very simply sometimes I think, is the voltage induced, or the magnitude of the voltage is choose. We'll forget about the negative. For simplicity, is equal to the number of turns times the magnetic field strength times the area divided by time, and we can put in front of it a change in any one of those divided by, well, the change in time. Time is always changing, and that's how we can also express that.